Okay, thanks Samuele for the introduction. Thanks to all of the organizers for doing this event for us. And of course, thanks to all of you for listening to this talk. As Samuele said, today we talk about conservativity. So first thing to do, let us recall what conservativity is, at least in the framework of dependent type theories. So suppose that we are given two dependent type theories, T1 and T2. And let us assume that the rules of T1, so the inference rules, the type constructors of T1 are contained in T2. But let us assume that they do not coincide, so that there are actually some judgments that T2 infers and that the T1 is not able to prove. Okay, even in this situation, we can still ask ourselves whether the two theories prove the same statements. So if you interpret the types of a dependent type theory as a statements, and the terms of these types as proofs of the statement, then this property corresponds to asking that, to the property that the theory T1 considers a given type, capital T, inhabited as long as it is inhabited according to T2. So in other words, if T2 proves a term judgment A lives in T, then T1 proves the same thing. So it also finds it is also able to build a term, let us call it A tilde, that lives in T. When this happens, we say that T2 is conservative over T1. So meaning that, I guess, if you reinforce the rules of T1 by the rules of T2, you do not risk to modify, namely to increase the deductive power of T1. You can assume you are working in T1, use the rules of T2, and still get results that are true in T1. So for instance, a conservativity result that appears in the literature is the following. T2 is an extensional type theory, and the T1 is an intensional type theory with some fundamental extensional assumptions, like for instance that any loop P is propositionally a reflexivity. With these two theories, you actually have a conservativity result. T2 is conservative over T1. And the proof is contained in this work by Hoffman of 1996, over which this talk is based. In fact, in this talk, we consider T1 to be an even farther weakening of the intensional type theory. Namely, we assume that T1 has propositional ID types that now we will talk about. Briefly, without going through the rules. Intensional ID types that we all know. These are the ID types of Per-Martin-Löf dependent type theory. There is a formation rule. When you have two terms of the same type, you can form their ID type. You have an introduction rule. If you plug in the same variable in both hand sides, then there's a choice of a term R of X. There's a path elimination rule that tells us that if we are given a statement, capital C, depending on a general path, and if we have a proof of that statement C, so a term that here I call Q of X, for C in case where P is a reflexivity, then you actually have a proof that here I call J for the general statement. So for the statement C, dependent on a general path P. And the computation rule tells us that this new proof J coincides with the one in the hypothesis Q if in place of P you plug in the reflexivity. What do we do today? We do not require the computation rule to be strict, to be a judgmental identification of two terms, but we require something less. Okay, so in place of the judgmental ruling, in place of the computation rule in judgmental form, we just require its propositional weak version, that is that there is some term that inhabits the corresponding ID type. This is what we require. These are the propositional ID types. We require that they exist in our type theory. ID types were considered, for instance, in 2014, in a cubical setting. These authors were trying to produce a model of per Martin-Löf dependent type theory. And in this case, there was no way of making the judgmental rule of the ID, of making the computational rule of the ID types strict. It only appeared in propositional form. Then there's this very important work by Benno van den Berg, in which he produces a notion of semantics for propositional identity types, which is based on this notion of path category. And more recently, Raphael Bouquet was interested in comparing type theories having weak equalities, so propositional equalities, to the corresponding type theories having strict equalities. So this was just a survey on where propositional ID types appear in the literature. In a similar flavor, we can consider the same form of weakening for, but here I guess you do not see the last line. Okay, this is, anyways, no worries. Propositional dependent sum types, thanks Samuele. Dependent sum types also have a computational rule, right? And again, we do not require, in this case, to have it in judgmental form. We just require it in a weaker form, that there is a term that inhabits the corresponding ID type. So now we can state the aim of the talk. We let PTT, for propositional type theory, to be a dependent type theory with propositional ID types, propositional sigma types, and propositional pi types. And our aim is to compare it to extensional type theories, looking for a conservativity result. The argument is completely semantical, and in detail we use the soundness of the semantics provided by the notion of category with attributes. Even though any other, I'm pretty sure that any other semantics would have worked as well. So if you prefer to use natural models, comprehension categories, I guess the same argument can be adapted. Now I would like to state the result before briefly going through the proof. And in order to do this, I needed to introduce the following notion, the notion of simple type. We say that a type judgment, capital T, of PTT, is simple if it belongs to the smallest family, curly f, of type judgments of PTT, closed by the following clauses. The first one is that all the basic type judgments of PTT, which are H sets, which happen to be H sets, need to belong to F. And the second condition is that the family is closed up to the formation rules of id, pi, and sigma. So basically, you consider the simple types, the simple basic types, sorry, the basic H side, again, the basic H sets of PTT, okay? And you close them by equality, dependent product, and the dependent sum. What you get are the simple types. Now, let us consider finally an extensional type theory, which we build in the following way. Okay, we will call it ETT. At first, let us say which are the basic types of ETT. These are just the basic H sets of PTT. So we consider an extensional type theory having a basic type, so a type which is not given by type constructors, an axiom, for any basic H set of PTT. And the same for basic terms. If we have a basic term living in a basic H set of PTT, then we require it to exist even in our extensional type theory. Okay, so basically this is the extensional type theory generated by the axioms, by the simple axioms of PTT, simple types of PTT, and the simple basic terms in these simple basic types. And now we can actually interpret ETT, which we can actually interpret the simple type judgments of PTT inside ETT. We can interpret the simple context, the simple type judgment in simple contexts, and the term judgments of PTT of some simple type in simple context. Let us call these 3 points the simple fragment of PTT from now on. So what is the simple fragment of PTT? It's just the simple types, the simple context of PTT, the simple types of PTT, and the terms living in some simple type of PTT. This is, for this fragment of PTT, you can define an interpretation in ETT, which we denote as a module. Then the result is that ETT is conservative over PTT relative to this family of simple types. Meaning that if we are given a simple context gamma of PTT and a simple type capital T in this simple context, assuming that ETT proves the interpretation of T, so assuming that ETT is able to build some term A in the interpretation of T, then so does PTT. PTT infers that there is a term, let us call it A tilde in T. And moreover, once you interpret A tilde in ETT, then ETT is not able to distinguish it from the term that ETT provides. So basically, it doesn't distinguish between the given proof and the proof that PTT provides. So let us briefly make this result. What does it mean? It means that despite PTT is actually weaker than ETT, because there are things that ETT proves and PTT doesn't, there is an interesting family of type judgments, namely the simple ones, where the two theories have the same power. Okay, and one can argue that this is a bit informal. What I'm saying is informal, but one can argue that simple types is what really matters in a dependent type theory. Why? Because in a dependent type theoretic foundation, when you do concrete mathematics, constructive real analysis, whatever, you only care about H sets. Like R is provably an H set, or I don't know, if you want to do abstract algebra, then the carrier types are all H sets, and most of the properties that you want to prove can be stated as H sets. And the simple types are not all of the H sets, because okay, for sure, simple types you can prove by induction on their complexity that they are all H sets. Usually, there are in a dependent type theory there are also some H sets which are not simple types. But we can say that most of the H sets that one cares about are simple types. In particular, if PTT, here we are working very generally. PTT has a very general family of basic types. But you know that in order to have a foundation of constructive mathematics, you only need 3 of them, maybe 4. Yeah, 4. You need the empty type, the singleton type, the number 2, and the natural numbers object. This is enough. Well, if PTT has only these 4 simple types, only these 4 basic types, these are provably H sets in PTT. So in this case, which is enough to give a foundation of constructive mathematics. In this case, PTT only has H sets as basic types. And so in this case, it would have a full conservativity because there's no distinction between basic types and basic types which are H sets. Any basic types is an H set. So in that case, you would have a full conservativity result. Okay, this was to briefly comment this result, what it can be useful for. And now I would like in the remainder to briefly go through the proof without entering too much through the details. So in this case, I decided to use the notion of a category with attributes to provide a notion of semantics for extensional and propositional type theories. Greta this morning already told us how the semantics works, but in the framework of categories with families of display maps, but nothing really changes. The idea is that what is a category with attributes? You are given a category C, whose objects we call semantic contexts, right? Gamma, delta, and so on. Then you want to give semantic types in this context. So you are given a pre-sheaf TP, which sends any context gamma into the family of its semantic types, which I denote with capital Latin letters, A, B, so on. Then you can extend the context with types in that context, right? Semantic context extension. And then you are given a family of display maps, which is natural from the semantic context extension to the growth and deconstruction associated to TP. And moreover, it's not just required to be natural, but it is also required to be Cartesian. This is very important to model a strict notion of substitution. In my structure, we define the semantic terms of a given semantic type A to be the sections of the corresponding display map. Because, as we saw even this morning, in the syntax of a dependent type theory, the terms of a given type are in bijection with the sections of the corresponding display map. So now we do exactly this thing. We define them to be the sections of the display maps. Categories with attributes are models of dependent type theories, because if you are given, you can really extend the substitution to terms. If you are given a section A of a given display map, PA, so a semantic term A of a type capital A, then there is unique A section of a PAF making the upper square commute. And we define A of F to be the substitution of a given morphism of context F inside the term A. So in this way, you, up to defining how to interpret any judgment of a dependent type theory, one can prove that this notion of substitution models all of the rules of the substitution of per Martin-Löf dependent type theory. So this provides a notion of sound semantics for any dependent type theory, up to giving a choice of the basic types and the basic terms. And of course, you can specialize this notion of semantics to provide semantics for extensional, intensional, propositional type theories. You just need to specify some choices of semantic types and semantic terms in such a way that the type constructors that you need are modeled. So now I can talk about the proof strategy in a few minutes. The idea is that you exhibit a model M of ETT, okay? And of course, if it is a model of ETT, it is also a model of the simple fragment of PTT, because any model of an extensional type theory is also a model of a propositional type theory. It is also a very special one. So you consider a model of a model M of ETT, okay? And you would like it to be to have the following property with respect to the simple fragment of PTT. We want that the interpretation of the simple fragment of PTT inside this model is surjective, okay? So that what would we like? That any semantic context of M is the image of some simple context of PTT. That any semantic type of M is the image of some simple type of PTT, and that any section of M, of a display map of M, is the image of some term of PTT. We would like M to have this property. Now I tell you why. Assume that we have such a model. So a model with this surjectivity property. Now we can, if we have such a model, we can actually deduce conservativity in this way. Assume that you have a simple type judgment, capital T, okay? And this in PTT, right? Now interpret it in ETT and assume that there is some proof of the interpretation in ETT, which here I call small a. So since M is a model of ETT, it needs to believe this judgment, okay? Which means that there is some section, right, of the corresponding display map associated to the interpretation of T, right? But M has the property that the interpretation of PTT is surjective, right? So this section will also need to be the image, okay, of a judgment, of a term judgment in PTT, right? Because M has this property of a surjectivity of the interpretation of PTT. So there is some simple term judgment, B, in PTT, which is sent in that precise section, okay? And then some initiality argument, delta needs to be exactly gamma, and S needs to be exactly T. So PTT finds a term B, which lives in T. With the hypothesis, I tell you again that the same happens for the extensional type theory. Okay, so this is how you prove the conservativity result. Right. Well, I guess there's no time to go through the construction of M, but let me just say that, of course, the idea is that you want to build a quotient, to perform some quotient of the syntax of PTT, right? In such a way that any path is identified with the reflexivity loop. But you cannot just do that, otherwise you lose all of the dependent type theoretic structure, right? So basically the rules of the strict substitution. So it would not be a model anymore. If you want to think category theoretically, you will not get a category with attributes with the Cartesian natural transformation. With maybe the natural transformation is still natural, the family of display maps, but for sure it will not be Cartesian. You would have several possibilities to define the substitution, and this we do not want. So the idea is that you have to identify paths with reflexivities, but at the same time maintaining the structure of the category with attributes. So you need to define a thing that is called canonical homotopy equivalencies between contexts in such a way that these two properties, once you quotient, are satisfied. I will stop here. Thank you so much.
Okay. Is there any question?
Thanks for the talk. So I was wondering about this initiality that you use in the proof,
right?
That you mentioned before. Do you mean like that? So is that the initiality of the model M?
No, initiality of the syntax of ETT. because the syntax of ETT can be
Okay.
made into a category with attributes,
Right.
which is the initial among.
Okay, so you use that initiality.
Yes.
Okay. All right, thanks. And then maybe a clarification with the basic type judgment. You mean one in the empty context? Or
No.
what do you mean by basic?
Usually, yeah. Usually they are given in empty context, right? I mean, in general, I mean types that are given that are not the result of the application
Okay.
of a sigma
So
pi
like the
or
atomic
equal.
predicates.
Yeah, basically the axioms of the rules without the premise, let's say.
And you have not considered what happened with the universe?
No, that's right. I didn't consider with the universe, which in fact, that is also needed to provide that is why before I said that what I was saying was not formal when I talked about foundations,
Right.
because of course to give a foundation, you also need a tower of universes, right? Right, it should be done with a tower of universes as well, but I didn't consider it still.
Okay, thanks.
Thanks.
I have more questions, but maybe...
Third question. Can I ask you just about this last construction? So it is syntactical, but you have to. So do you have to use some choice principle in the meta theory to?
Yes, yes. Up to now, yes, but from a discussion with Milli Maietti, it seems that one should be able to. I mean, I still have to see whether it works in this framework, but Milli Maietti and Michele Contente in a simple in a similar framework have a way to avoid the use of some sort of choice in the meta theory, which I was suggested to see if it is applicable even in this framework.
Okay,
Thanks
you.
for the question.
So let's thank the speaker again.